Before anything else, there was a mystery. Before stars, the whole story was already written by something you couldn't see. Dark matter. It's the ghost that built the universe. It built the first galaxies out of almost nothing. A cosmos that was just darkness, and then it made the first light. That invisible force is the reason you're here. It shapes the foundations of everything. The universe was very young then, only about 380,000 years old, and it wasn't dark at all. It was this bright, uniform sea, a plasma where light and matter were just constantly colliding. That was the first light, and we can still see it. We see it now as the cosmic microwave background. It's like a snapshot of how things were back then, and what it shows is that the early universe was incredibly smooth. The density, from one place to another, the differences were tiny, just whispers. Those whispers were quantum ripples. They got frozen in right at the very beginning. And they were the only seeds for everything, every galaxy, every star, but by themselves they were too weak. Gravity acting on imperfections that small. It would have taken much longer than the universe has existed to make anything. It would be like trying to build a mountain from a breeze. For those seeds to grow, they needed something else. A foundation, a kind of hidden architecture with more mass, something with a stronger gravitational pull to gather the ordinary matter. The stage was set. And it was empty, waiting for something invisible to step into the light. We call that hidden architecture dark matter. To see how it built the first galaxies, we need to know what it is. And what it isn't. It isn't made of atoms. It isn't what you or I or any star is made of. It doesn't absorb light. It doesn't reflect it. It doesn't give off light. It's completely dark. If you held a piece of it, you wouldn't see it. Your hand would go right through. The only reason we know it's there is its gravity. It has this immense pull. It's a ghost, but a ghost with weight. Think of the universe as a construction site. The galaxies are the skyscrapers we see shining. But under each one, in the darkness, is a foundation, a framework of dark matter. Without that support, the whole structure collapses. It would never have been built. This invisible stuff is about 85% of all matter. Everything we can see, planets, nebulae, us, it's just the decoration, the trim on a reality built by something else. So what is it? The main idea is something called weakly interacting massive particles, WIMP. The name says it. They're particles with mass, so they have gravity. And they are weakly interacting. They barely talk to normal matter or light. They just pass through, silently. Trillions pass through you every second. You feel nothing. That aloofness was its superpower early on, because the bright plasma, the ordinary matter and light, was chaotic. It couldn't clump. But dark matter was free. It only felt gravity, and gravity started pulling it into the faint ripples from the Big Bang. In the total darkness before the first stars, this invisible substance was already gathering. It was drawing the blueprint, making gravitational wells in space, places where the first light would eventually, inevitably, fall. Dark matter was moving freely. But ordinary matter was stuck. It was caught in this constant, chaotic dance with light. For almost 300,000 years after the Big Bang, the universe was just this searing hot soup. Protons, electrons, and photons, light, everything was so densely packed, so energetic, that particles were constantly colliding. An electron would try to settle near a proton, and then a photon would come in and knock it away. That created an immense outward pressure, a force pushing back against gravity's inward pull. It was a stalemate. Ordinary matter, what we call baryonic matter, it couldn't clump. It couldn't collapse to form stars or galaxies. It was like trying to build a sandcastle in a hurricane. You'd get a little pile together, and the wind and waves would just blast it apart. Dark matter didn't feel any of that. It was the other runner in the race, completely unburdened. While ordinary matter was tangled in that parachute of radiation, dark matter was just responding to gravity. It felt those subtle tugs, those primordial quantum ripples, those tiny whispers of unevenness from the very beginning. And with nothing to push back, it could start to move. It could begin to flow into those faint, denser regions. This was the first mover advantage, but on a cosmic scale. In the darkness before the first spark, the invisible architecture was already being assembled. Vast, tenuous webs of dark matter began to form, with dense knots halos at their intersections. These halos were gravitational wells, deep pits in the fabric of space-time. But they were empty pits, sculpted in darkness, just waiting. The universe had to cool. It had to expand and thin out enough for that chaotic plasma to finally calm down. For the photons to stop bullying the electrons. That moment is recombination. The electrons finally combined with protons to form neutral hydrogen atoms. And suddenly, the universe went transparent. The light that had been trapped could finally travel. It streamed out in every direction. That light is the cosmic microwave background we see now. But more importantly, ordinary matter was finally set free. Free from the tyranny of radiation. The hurricane had stopped. Now the gas of hydrogen and helium was quiet and dark, and it began to feel the pull. The gravitational pull from those pre-existing dark matter wells. The invisible framework had been built in advance. Now the ordinary matter simply flowed into the scaffolds. It slid down those gravitational slopes, pooling at the centers of the dark matter halos. And it was here, in these deep, dark pits, that the gas could finally compress. It could get dense enough and hot enough to ignite. The first stars weren't born from chaos. They were born in the ordered traps laid by an unseen hand. The first galaxies didn't form alone. They were born inside a network, a structure that was already there, woven across everything. That's the cosmic web. It's not just an idea. It's the real skeleton of the universe, and it's made of dark matter. Think of a sponge, or the veins in a leaf, or frost on glass. That's the shape of the cosmos, a tracing of filaments stretching over billions of light years. Where those filaments cross, you get knots, hubs, and that's where the biggest galaxy clusters would eventually form. But for so long, this whole structure was dark. Just a ghost framework, a blueprint in gravity, waiting. This web wasn't random. It was a direct result of what dark matter is. Dark matter only responds to gravity. So as the universe expanded, those first tiny ripples became seeds. Gravity made them bigger. Dark matter, with no light to push against, moved toward those seeds. But it didn't just make blobs. It's like water on a window. It doesn't gather randomly. It finds the paths, it traces channels, it connects, it forms branches. Dark matter did that. It flowed along the shape of space-time, making rivers of invisible mass. Those rivers are the filaments. Where rivers met, they pooled. Those pools are the dark matter halos. They're the gravitational traps, the deep wells in space, and they were the necessary stage. Without them, the early gas, that quiet hydrogen and helium, would have just drifted. A thin, smooth fog, but the halos changed that. They were the focal points, the gathering places. The gas felt their pull and started to slide down those filament highways. It streamed into the halos, collecting at their centers. For the first time, normal matter was being gathered and compressed on a huge scale. The stage was set. The invisible skeleton was finished. The first actors, those vast clouds of pristine gas, were in place. But a stage and an actor aren't a show. Something had to happen. The gas had to change, it had to ignite, and to do that it faced a problem. The gas had to lose its energy, it had to cool down. Gravity pulls a gas cloud inward, compressing it. But that compression heats the gas. The heat pushes back out. So for collapse to really happen, for the density to reach nuclear fusion, the cloud has to lose that heat. It has to cool. In the early universe, that was the bottleneck. The gas was pristine, just hydrogen and helium, no dust, no heavier elements, and that simplicity was a problem. Today, clouds cool through molecules or dust grains. Back then, those didn't exist. The only way for that primordial hydrogen to cool was a very specific process. The hydrogen atom itself had to release energy. An electron orbiting its proton could make a tiny jump, dropping from a slightly higher energy state to a slightly lower one, releasing a single photon of light, a whisper of infrared. That was the only escape valve for all the gravitational heat, a painfully slow leak. This cooling process set the pace. It decided the size of the first clouds that could fully collapse. It dictated the mass of the very first stars, because only the largest dark matter halos could gather enough gas and hold it together long enough for this slow atomic cooling to work. The universe was ready to build, but it could only build giants. That first cooling process was a real challenge for the universe. You had this whole invisible structure. Dark matter halos shaped by gravity, pulling in huge amounts of clean gas. But that gas was hot. It got hot from falling into the gravity well. It's like compressing air. The compression makes it hot. That heat is energy, and it pushes outward against the inward pull of gravity. So for the gas to collapse into a star, it had to lose that energy. It had to cool down. Now that's easy today. Giant clouds have dust and complex molecules. They work like radiators, shedding heat very well. But the first clouds had none of that. No dust, nothing heavier than hydrogen and helium. They were pure and simple and really bad at cooling. Their only chance was a faint quantum process. Molecular hydrogen, not the single atoms but two hydrogen atoms bound together. This delicate molecule could do something. When it gets bumped and spun in the hot gas, it can let go of a tiny bit of infrared light. That light takes energy away into space. It's an incredibly slow process, like trying to cool a boiling pot by letting one photon escape every few seconds. But it was all they had. This created a bottleneck, a kind of cosmic gatekeeper. The cooling rate set the speed for everything. A dark matter halo had to be massive enough to pull in a truly enormous cloud. Only then would the density get high enough for enough molecular hydrogen to form, and for collisions to happen often enough, for that slow energy leak to actually beat the heat from the collapse. Scientists call that the minimum cooling mass. It was the threshold, the line between a cloud that just stays hot forever and one that can finally start to condense into a star. This connects the invisible to the visible. The properties of the dark matter halo, its mass, its gravity, set the timeline. A smaller halo might gather gas, but that gas would just swirl, hot and stuck. It couldn't condense. It had to wait. Maybe merge with other halos, grow in mass until it crossed that critical line. Only then could the cooling finally win. The gas could start to cool, to fragment, to condense into dense, cold knots. That first light wasn't a sudden switch. It was a slow, precarious process, governed by the delicate physics of a simple molecule and the immense, patient gravity of something unseen. The universe was holding its breath, waiting for the cooling to catch up. In those deepest gravitational wells, the universe crossed a line. The cooling finally won. The gas had been swirling and condensing for eons, and at its core it reached a critical density. A critical temperature, millions of degrees. The pressure became so immense it could overcome every repulsive force. And in that moment, for the first time since the Big Bang, nuclear fusion ignited. The first stars were born. We call them population 3 stars. They were nothing like our sun. They were cosmic titans, monsters made of pure hydrogen and helium. They could be hundreds of times more massive than our own star. A single star shining with the brilliance of a million suns. Their formation was the direct result of that long preparation. The dark matter halos had gathered the fuel. The slow molecular cooling had allowed it to condense, and then physics took over. Their lives were spectacular and brutally short. Burning at such ferocious rates, they exhausted their fuel in just a few million years. A cosmic blink, but in that blink they changed everything. They ended the cosmic dark ages. For hundreds of millions of years, the universe had been a dark, neutral fog. And these stars pierced that fog with torrents of ultraviolet light. That first starlight began to tear apart the neutral hydrogen atoms filling all of space. It stripped away their electrons in a process called reionization. It was like turning on the lights in a vast, dark room, watching the shadows flee. This was the dawn of the visible universe. Not a gentle sunrise, but a violent, glorious flash. A dawn that was only possible because of the silent, gravitational architecture built in the darkness before. The invisible had finally crafted something that could be seen. But these first stars were just the beginning. Their brilliant deaths would set the stage for the next act. An even more crucial act of creation. Those first stars, their brilliant deaths, that was the real catalyst. When they ran out of fuel, their cores collapsed. Supernova explosions, and these weren't just flashes. They were cosmic forges. In that heat, in that pressure, heavier elements got made for the first time. Carbon, oxygen, nitrogen, iron. The universe had been simple. Just hydrogen and helium. Now it was seeded with dust, with metals. That stardust was their legacy. And it changed everything, because the gas wasn't pristine anymore. It was enriched. And that enrichment solved the cooling problem. Dust grains, complex molecules. They radiate heat away so much better than simple hydrogen. So gas clouds could cool faster. They could fragment into smaller, denser clumps. The next stars didn't have to be giants. They could be smaller, longer-lived. Like our sun, the universe had found a new way to build, but that feedback wasn't all constructive. It was destructive too. Their ultraviolet radiation, it reionized the universe, but it also heated the gas around them. Immense temperatures. Hot gas has high pressure. It resists gravity. That radiation could push the gas away. Blow it right out of the small dark matter halo that gathered it. It's like a sapling growing leaves, and its first sunlight scorches the soil, dries up the water. The act of shining could starve its own cradle, and then the supernova. The explosive force, it could do more than enrich. It could disrupt the gas clouds completely, scatter them, eject them from those shallow gravitational wells. So the story gets complex here. For hundreds of millions of years, dark matter was in control. It built the stage. It dictated where gas would pool. But when that first star ignited, the rules changed. Baryonic physics entered. Light, heat, pressure, chemistry. It created a feedback loop, a dance. Gravity from the dark matter gathers gas. The gas forms stars. Those stars, through their radiation and explosions, heat the gas, enrich it, sometimes expel it. The gas future stars need. This loop began to regulate everything. How many stars a small protogalaxy could form? How quickly? Whether growth was steady or stunted by its own first light. The invisible hand of dark matter built the first theaters. But now the actors were rewriting the script, shaping the growth of the first true galaxies in a way dark matter alone never could. We can't see dark matter. We can't go back and watch it happen. So how do we know any of this story is true? The evidence comes from a different kind of lab, a digital lab. The story of the first galaxies is being written inside supercomputers. Researchers take what we do know, the laws of physics, that precise baby picture of the universe, the cosmic microwave background. They feed all that into a machine. They ask one monumental question. Given these rules and this starting point, what happens next? The answer comes from cosmological simulations, entire digital universes born from equations. They evolve over virtual billions of years. They model two things: the dark matter, flowing and clustering under gravity, and the ordinary matter with all its complex physics, gas, pressure, cooling, stars. The computer calculates the gravitational pull of every piece of dark matter on every other piece. It tracks how gas flows, heats, cools, and ignites. It's a mathematical experiment on a scale we could never run in reality. Projects like Illustris TNG have done this. The Cosmic Dawn project, and what they show is breathtaking. You can watch it. A smooth, virtual cosmos begins, then, like ink in water, dark matter starts to trace patterns. Filaments emerge, stretching across the void. Knots form where they cross. These are the dark matter halos, and right on cue, the simulated gas responds. It streams along those filament highways. It pools at the centers of the halos. Dense knots of gas begin to glow. The first virtual stars ignite. What's astonishing is how closely these digital creations match the real night sky. The simulations produce galaxies with the right shapes, the right sizes at the right distances. They show small protogalaxies merging to form larger ones. They show how supernova explosions can blow gas away, stunting growth in small halos. They even show the large-scale structure, the cosmic web of galaxies that our telescopes map. It all emerges from the code, but only if you include the dark matter. If you run the same simulation with only the ordinary matter we see, the universe that forms looks nothing like our own. The structures are too weak. They form too late. They're too small. The invisible scaffolding isn't just a neat idea. It's a necessary ingredient. Without it, the digital universe fails. These simulations are more than just pretty movies. They're a crucial test. They let us rewind the tape of cosmic history and press play over and over. We can tweak the rules each time. What if dark matter was slightly different? What if the first stars formed a different way? The simulation shows us the consequence. By comparing the end result of these virtual runs to our actual, observed universe, we can see which theories hold up. It's how we connect the invisible past to the visible present. The story of the first light isn't just written in the stars above. It's being decoded in the silent hum of a supercomputer, one calculation at a time. The real sky is the test, not a supercomputer. The evidence is out there in the dark. For a long time, those first galaxies were just theory, just equations. But now we have a time machine, the James Webb Space Telescope. It was built to see far, to see back, to see the cosmic dawn. Its power is infrared vision. Think about the light from those first galaxies. They're so far. The universe has stretched that light. It's been traveling over 13 billion years. That journey shifts the light. From visible to infrared, to our eyes it's invisible, but to Webb's mirrors it's a beacon. It can see that faint, redshifted glow. Stars from when the universe was an infant, a few 100 million years old. Every faint smudge in its deepest images, that's not just a galaxy, it's a message. A snapshot from when everything was being built. Studying these, astronomers aren't just looking at stars. They're reverse engineering dark matter. They measure a galaxy's mass. Its shape, how fast it forms stars, these are clues. A galaxy doesn't exist alone. It sits inside a dark matter halo. That halo's gravity dictates everything. How much gas it gathered, how fast that gas cooled, how well it held onto that gas against the violence from its own stars. So when Webb finds a galaxy, a bright, massive one from a shockingly early time, it asks a direct question. What kind of dark matter halo could grow that massive, that fast? Our models have to answer. The observations are the judge. Every new ancient galaxy is a data point, a piece of evidence in the trial. The invisible matter shaped the stage, and now we're seeing the actors it produced. Frozen in their youth. This isn't just theory anymore, it's a detective story, written in starlight that has traveled since the beginning. Dark matter and ordinary matter work together. But they do different things. Dark matter is like the architect. It draws the blueprints, it builds the foundation. Its job is gravity, a pure, immense gravitational pull. It creates these deep wells in space-time, stable valleys where everything else will gather. But dark matter is passive. It doesn't light up. It doesn't react to light. It doesn't form complex things on its own. It just sits there, an invisible skeleton. It defines the shape. Ordinary matter is the builder, the baryonic matter. The stuff of stars and planets and us. It's active. It feels that pull and flows into those wells. And once it's there, it gets busy, it collides, it compresses and heats up. It cools through intricate processes. It fragments, it condenses into stars, and those stars shine, they explode. They enrich the gas with new elements. That's feedback. It's dynamic, it's complex, often violent. The baryonic matter doesn't just fill the mold, it changes the mold. you can picture a mountain range. An ancient one, the dark matter is the mountains, the solid, enduring rock. Shaped over eons, it defines the landscape. It dictates where the valleys are, where the high points stand. The baryonic matter is the weather. The clouds, the rain, the rivers, the storms. The mountains force the air to rise. They create clouds on their slopes. They channel the rivers. They create microclimates. But the weather is a swirling, dynamic system. It erodes the mountains over time. It deposits soil. In a storm, it can trigger a landslide. It reshapes the slope. One sets the stage, the other performs. One is the permanent setting. The other is the ever-changing drama. In the early universe, this separation was absolute. Dark matter halos formed first, in the dark. They were the gravitational anchors, then the gas flowed in. But once that first star ignited, the baryonic weather system began. Its radiation heated the surrounding gas. That made it harder for more gas to fall in. Its supernova explosions could blow gas clear out of a small halo. This feedback began to regulate the growth. A small dark matter halo might have its gas supply cut off by its own first stars. It would stall. Its growth would depend on merging with another halo, or waiting for new, cooler gas to slowly seep back in. The invisible mountain was still there. But the storm had scoured its slopes clean. That's the central drama. Without the dark matter backbone, there would be no places for the gas to collect. The universe would be a thin, smooth fog. No focal points for stars. But without the active, complex physics of the baryons, those dark matter wells would remain forever dark and empty. Just silent pits in space. The story of the first light isn't about one or the other. It's about their intimate, billions of years-long tango, a dance between the invisible and the visible, where gravity builds the stage and starlight writes the play. The architect itself is still a mystery. We see what dark matter built, but we don't know what it is. And that unknown changes how the first galaxies formed. If you're building a house, the foundation matters. Is it bedrock or loose gravel? Both hold a house, but they settle differently. They crack in different ways. They support different structures. Dark matter is like that. Its particle nature dictates how it clumps, especially on the smallest scales. And the smallest scales are where the first, tiniest galaxies were born. For decades, the leading idea has been cold dark matter. Cold doesn't mean temperature. It means slow. These particles would have been moving sluggishly in the early universe. That slowness is key. It lets gravity pull them into very small, dense clumps first. Those tiny clumps then merge to form bigger ones, a bottom-up process. This model is spectacularly successful. It predicted the cosmic web, the vast filaments and clusters we see. But when we zoom in, to the scale of our own galaxy's backyard, there's a tension. Cold dark matter simulations predict our galaxy should be surrounded by hundreds of small, dark satellites. Swarming like bees, we only see a few dozen. That's the missing satellites problem. It's a clue. Maybe dark matter isn't cold. Maybe it's warm. Warm dark matter is a different candidate. These particles would have been moving faster in the early universe. That extra motion acts like a smoothing force. It washes out the very smallest clumps. It prevents those tiniest dark matter halos from ever forming. In a warm dark matter universe, structure forms top-down. The first things to appear are the filaments and sheets. The small clumps come later or not at all. So in this picture, the Milky Way would naturally have far fewer tiny satellites. The problem might just vanish. But there's a trade-off. If the smallest dark matter halos are erased, then the very first galaxies, which need those halos as anchors, might form later. Or they might look different. Their stars might be born in a different pattern. This is why the cosmic dawn is more than an astronomy story. It's a particle physics lab. The properties of those earliest galaxies we see with Webb, how many there are, how small they can get, how early they appear. These are direct fingerprints. They can tell us if the primordial dark matter was cold and slow, or warm and fast. Each ancient galaxy is a data point in a grand experiment. an experiment that started over 13 billion years ago, when the nature of an invisible particle decided the fate of the first light. We are using telescopes to do particle physics. By looking at the oldest structures, we are peering into the fundamental rules of reality. The quest to understand the first galaxies has become a search for the identity of the hidden architect. The whole idea of dark matter, it's a huge assumption that we have to invent something invisible to make the cosmos make sense. But maybe the problem isn't missing matter. Maybe it's gravity itself we don't fully understand. That's what theories like Mann propose. Modified Newtonian dynamics. It starts with a simple observation. Newton's law of gravity works perfectly in our solar system, where gravity is strong. But it was never tested where gravity is extremely weak, out at the edges of galaxies. So what if the law changes there? You tweak the math, and then the stars orbit at the speeds we see without any extra mass. No dark matter halo, just a change to gravity. It's a compelling idea. It solves the rotation problem right in front of us, but the universe has more to it than that. Explaining one galaxy's rotation is just one piece. The real test is the beginning, the formation of the first galaxies. That's a profound challenge for modified gravity. In the standard story, dark matter had an advantage. It was aloof. It could start clumping right away in the dark while ordinary matter was stuck. It provided a head start, a gravitational scaffolding. Modified gravity doesn't have that separate actor. There's only normal matter, and in the early universe that normal matter was paralyzed by radiation pressure. There was no invisible architect to build the stage first. So in a Mann universe, how do you get those first gas clouds to collapse so quickly? How do you form galaxies as early as we see them? Then there's the cosmic microwave background. Those tiny ripples, their specific size and distribution. They match a universe where most of the matter is cold and dark. Perfectly. Trying to reproduce that pattern with only normal matter and a tweaked gravity law has been incredibly difficult. So the early universe becomes the proving ground. It's a cosmic crime scene. The evidence is frozen in the first light. Did an invisible substance shape that light by gathering gas into pools before the first stars? Or can a revised law of gravity alone explain it? The rapid, structured emergence of galaxies from a formless dawn. This isn't just a historical question. It's the key evidence. We're forced to choose between two ideas. Either the universe is mostly made of something we cannot see, a ghost that built everything, or our grasp of gravity is incomplete on the largest scales. Both possibilities are staggering, and the verdict will be written in the ancient light of the first galaxies. There's another mystery here. What if those first dark matter halos didn't just hold gas? What if they held something else, a different kind of seed? Something from the universe's first violent moments. Primordial black holes. These aren't the ones from dying stars, those came later. Primordial black holes are a hypothetical idea. They could have formed in the very early universe. From patches of space that were incredibly dense, a kind of cosmic imprint, left over from the first fraction of a second. And some scientists think these primordial black holes could be part of dark matter. Maybe not all of it, but a portion. If that's true, then the invisible architecture wasn't just a smooth substance. It was also studded with these pinpoint singularities. These tiny, bottomless pits of gravity. So imagine a dark matter halo forming, a vast invisible cloud, and inside it, a single, incredibly dense point. A primordial black hole, with the mass of a mountain or a planet. It would naturally sink to the very center of the halo. It becomes the ultimate gravitational anchor. A fixed point. Everything else organizes around it. That changes the dynamics completely. When the first gas clouds flow into the halo, they aren't just falling into a diffuse well. They are being drawn toward this intense central knot. The black hole's gravity would accelerate the gas, heating it even more as it spirals inward. That could trigger intense, early bursts of radiation. Or it could help gather and compress the gas faster than gravity alone could manage. It adds a powerful, focused engine to the heart of the system, and this idea might solve another puzzle. In the centers of nearly every large galaxy, we find a supermassive black hole. Our own Milky Way has one. These monsters weigh millions or billions of times the mass of our Sun. How did they get so big, so fast? If they started from the collapse of a single, massive first star, they'd have to grow at an almost impossible rate to reach the sizes we see in the early universe. But a primordial black hole provides a head start, a ready-made seed, already in place when the first gas arrives. It could begin feasting immediately, growing steadily over cosmic time into the behemoth we observe. The invisible hand that shaped the galaxy also planted the seed for its darkest heart. So the narrative deepens. The first structures may have been shaped not by one invisible force, but by a partnership, a diffuse sea of dark matter particles, weaving the cosmic web and sculpting the halos. And within those halos, perhaps, these primordial black hole seeds, acting as gravitational nuclei. One provides the grand stage, the other provides a focal point on that stage. Together, they could have directed the collapse of the first gas clouds with even greater efficiency, adding a new layer of complexity and power to the dawn of light. The story of the first galaxies becomes a tapestry, woven from multiple kinds of darkness, each playing a distinct part in bringing about the visible cosmos we call home. The story of the universe is a timeline of structure. It begins with a whisper and ends with cities of light. The first chapter happened in a fraction of a second. That was cosmic inflation, when the universe expanded faster than light. And in that frantic stretching, quantum ripples got frozen into reality, like the faintest texture on a balloon, imprinted just as it starts to inflate. Those were the seeds, the only imperfections in a perfectly smooth cosmos. Without them, gravity would have had nothing to hold on to. The universe would have stayed a featureless sea. But those quantum whispers were magnified to cosmic scales. They became the faint overdensities, places where space was just slightly denser. That was the blueprint. Invisible but real. For the next several 100,000 years, not much seemed to happen structurally. The universe was a bright, opaque plasma, but in the darkness the game had already started. Dark matter, feeling only gravity, began to respond to those overdensities. Within the first million years, while ordinary matter was still locked in a dance with light, dark matter was already flowing. Silently, it began to pool into those denser regions. It was tracing the ghostly outlines of the future cosmic web. The foundation was being laid in total darkness, long before the first spark. Then you reach a critical milestone, around redshift 20 or 30. That's when the universe was only about 100 or 200 million years old. By then, the first dark matter halos had grown massive enough. They crossed that critical threshold, the minimum cooling mass. Their gravitational wells were deep enough to pull in vast clouds of pristine gas, and to hold onto them long enough for that slow, molecular hydrogen cooling to work. Inside these halos, the gas finally condensed, it fragmented, and then ignition. The first stars, the population 3 Titans, blazed into existence. Their light ended the cosmic dark ages. That was the moment the invisible architecture finally became visible. But one star doesn't make a galaxy. The timeline continues, driven by a relentless process. Hierarchical merging. Small dark matter halos, each maybe holding its own cluster of early stars, began to drift together. Drawn by their mutual gravity, they collided and merged. Like droplets on a window pane, they coalesced into larger and larger structures. Over the next several 100 million years, these mergers built up the first true protogalaxies. It was a messy, violent construction site, and all the while stellar feedback was at work. Those first stars lived fast and died in supernova, polluting the primordial gas with the first heavy elements. That enrichment changed everything for the next generation. Gas could now cool faster, fragment more easily, and form smaller, longer-lived stars. The universe was learning how to build with greater efficiency. So the full journey is astonishing in its simplicity. From quantum noise, amplified in an instant, to an invisible gravitational scaffold assembled in the dark, to the first points of light, to the mergers that built larger islands of stars, and finally to the enriched, complex ecosystems where galaxies like our own could form. It's a step-by-step process, a chain reaction set in motion at the beginning. The persistent, patient pull of dark matter is the through line. It's the force that took random noise and, over billions of years, organized it into the cosmic metropolises we see glittering today. The deeper we look, the more puzzles we find. Our story of the first galaxies is compelling, but it's not complete. There are several major mysteries, and they challenge the models we've built. The James Webb Space Telescope, our time machine to the dawn, delivered a shock. It found galaxies from when the universe was only a few 100 million years old. And some of them aren't just infant smudges. They're surprisingly massive. They're bright, structured, forming stars at a ferocious rate. According to our standard timeline of dark matter halo growth, these galaxies shouldn't exist yet. Their dark matter foundations, according to the simulations, shouldn't have had enough time to gather that much mass, to pull in that much gas. It's like finding a fully grown tree in a forest we just planted last season. This is the early massive galaxy problem. It suggests something in our recipe is off. Maybe star formation in those primordial clouds was far more efficient than we thought. Maybe the first stars didn't blow their gas away as violently, allowing for quicker, more sustained building. Or it could point to the nature of dark matter itself. If dark matter was slightly warmer with faster-moving particles, it might have formed those first massive halos a bit sooner, giving these galaxies a head start. Each ancient galaxy Webb finds is a clue, and right now, some of those clues are pointing to chapters we haven't yet written. Then there's the transition itself. We talk about the first stars, and then we talk about the first galaxies. But that leap isn't simple. A single, brilliant titan is not a galaxy. A galaxy is a vast, gravitationally bound city of billions of stars, with gas, dust, often a central black hole. How do you get from one to the other? This involves the most complex, messy part of the story, baryonic physics. It's about how those first supernovae not only enrich but also disrupt. How gas cools, falls back, and forms second and third generations of stars. How small protogalaxies, each with its own dark matter halo, dance together, merge and stir their stellar populations into a single, larger system. This is a ballet of gravity, hydrodynamics, radiation, and chemistry. And we're still decoding the steps. The cosmic dawn didn't switch on like a single lamp. It was a slow, patchy, chaotic awakening across the universe, and we're only beginning to map its true chronology. These unsolved problems aren't failures. They are guideposts. They remind us that the universe is always more inventive than our theories. The secrets of the first light are still held close, waiting for the next observation, the next simulation, the next leap of understanding to bring them into view. The gas that made the first stars was only a small part of the total. Most ordinary matter never got into those early halos. It stayed out in the spaces between galaxies. That's the intergalactic medium. It's not empty. It's an extremely thin sea of hydrogen gas, and it might seem diffuse, but it's not random. Its structure is an imprint of the dark matter web. This gas doesn't just sit in the gaps. It traces the filaments. It flows along those invisible gravitational paths, pulled by the same dark matter that built the galaxies. So the cosmic web isn't just a dark matter skeleton. It's outlined by a faint fog of hydrogen, tracing the shape of the invisible. This medium is far from pristine. It's been changed by the galaxies it helped create. Those first massive stars, when they died, their ultraviolet radiation did more than reionize the universe. It heated this intergalactic gas to tens of thousands of degrees. Their supernova blasted heavy elements out into the vast spaces: carbon, oxygen, silicon. So this reservoir is now warm and chemically enriched. It's different from the cold, pure hydrogen of the early cosmos. and it keeps evolving. As galaxies shine, their radiation keeps the gas hot. That stops it from easily collapsing into new stars. It's a feedback loop on a universal scale. Galaxies regulate the very reservoir they feed from. That reservoir is essential. Galaxies aren't closed systems. They don't just form and then run on their initial fuel. They grow over time by slowly sipping from this intergalactic sea. Cooler, denser clumps of gas within the filaments get funneled along the dark matter scaffolding. They stream into waiting galactic halos. This process is called accretion. It's how a galaxy gets fresh fuel to form new stars across billions of years. Our own Milky Way is still doing this, quietly gathering material from the cosmic web. So a galaxy's story isn't a single birth event. It's a long, sustained relationship with its environment, guided by gravity's invisible hand. We can't see this tenuous gas directly, but we have a tool to map it. Quasars, the brilliant cores of ancient galaxies powered by supermassive black holes. They act as cosmic lighthouses. Their intense light travels across the universe to us. On that long journey, it passes through the intergalactic medium. Atoms in that gas absorb specific wavelengths of that light. When we break the quasar's light into a spectrum, we see a forest of dark absorption lines. Each line is a fingerprint. It tells us what element absorbed the light, how much is there, and its redshift, which tells us how far away that patch of gas is. It's like taking a core sample of the universe along a single billion light-year line of sight. By studying thousands of these quasar spectra, astronomers can build a three-dimensional map of the intergalactic gas. And because that gas follows the gravitational contours of the dark matter web, this map is also a map of the invisible framework itself. It's a shadow picture. We see the silhouette of dark matter's structure, painted in missing light. This technique gives a complementary view to galaxy surveys and cosmic microwave background measurements. It confirms that the vast spaces between the bright islands aren't empty. They're organized, shaped, and defined by the same mysterious force that sparked the first light. A silent ocean whose currents are ruled by darkness. A dark matter halo isn't just a smooth cloud, it's more intricate than that. Our best simulations show they have an internal architecture. A kind of ghostly anatomy. The density isn't uniform, it peaks sharply at the very center. That's the intense gravitational core, and then it tapers off. It extends far beyond the galaxy's visible edge, like a vast fog. This density profile, it's not arbitrary. It's a mathematical signature, a fingerprint of how dark matter behaves under gravity. That invisible gradient sets the rules for everything inside it, but it goes deeper. In a large halo, there's a sea of substructure. Countless smaller clumps called subhalos orbit within the larger one. They're like asteroids orbiting a planet, but on a much larger scale. They're relics, fossils of the merging process. Each one is a survivor, a smaller structure that was swallowed during a merger but hasn't been torn apart yet. They drift like ghostly islands in the dark matter sea. This substructure has real consequences. Think of a large halo as a city. The central peak is the downtown core. The subhalos are like neighborhoods, each with its own local gravity. When gas flows in to form stars, it doesn't just fall smoothly to the center. It encounters these orbiting subhalos. Their gravitational tugs can perturb the gas streams. They stir the pot, cause turbulence that affects where the gas settles. It can influence the final shape of the galaxy's disk. And some of these subhalos might be massive enough to hold onto their own gas. Their own miniature gravitational wells could trigger star formation. Tiny, isolated pockets of stars. That could explain the ultra-faint dwarf galaxies we see orbiting larger ones like the Milky Way. They might not be primitive building blocks that failed to merge. They might be the luminous survivors of those ancient subhalos. They're stars shining from within a still intact shell of dark matter. So the final galaxy isn't just shaped by a smooth, monolithic halo. It's a product of a dynamic system, a central gravitational anchor, surrounded by a swarm of invisible perturbers, all working together to sculpt the flow of light-giving matter. The invisible foundation has its own complex geography, a hidden landscape that determines the visible world. That gas was pristine, no metals. The first stars were pure hydrogen and helium. And then they died, spectacularly. That changed everything. In their final moments, the heat and pressure fused those simple elements into heavier ones. Carbon, oxygen, nitrogen, iron. So the universe wasn't chemically simple anymore. Those new elements, what we call metals, were blasted out by the supernova shockwaves. They mixed with the surrounding gas, enriched it. That was the first cosmic recycling. The death of one generation became the raw material for the next. And it left a record, a chemical fingerprint. The pattern of this enrichment across the early cosmos is a clue. It didn't happen evenly, not a uniform sprinkle. The first metals were created inside specific dark matter halos, where those first stars lived and died. The supernova ejected them, but they didn't vanish. Their spread was guided by gravity, the pull of the original dark matter halo, and the larger filament it was part of shaped how far they traveled. They would flow along those invisible filamentary highways, seeding neighboring gas. So the distribution of the first metals paints a map of where the first structures were and how they were connected. By reading this ancient chemical map, we can trace the architecture of the early cosmic web. And we have a way to read it. Stellar archaeology. Our own Milky Way is ancient. It contains stars nearly as old as the universe. Stellar fossils. They formed from gas clouds enriched by just 1 or 2 generations of those first supernova. By analyzing their light with spectrographs, astronomers can measure the precise amounts of each element in a star's atmosphere. Its chemical composition is a frozen snapshot, a direct record of the gas cloud it formed from over 13 billion years ago. A star with almost no iron, but traces of carbon from a specific supernova type, tells a story. It suggests it formed from gas polluted by a single, particular kind of first star. A star with a different pattern points to a different progenitor, in a different dark matter halo. By cataloging these chemical signatures in the oldest stars, astronomers are doing reverse cosmic engineering, piecing together the population of those first stars, inferring their masses, the energies of their explosions, and by extension, the properties of the dark matter halos that nurtured them. Each ancient star is a time capsule, holding a chemical message about the conditions at the dawn of structure. This turns starlight into a forensic tool. The invisible hand of dark matter gathered the gas and enabled the first stars. Those stars forged the first metals. The pattern of those metals, preserved in stellar fossils, now lets us infer the shape and strength of that invisible hand. It's a chain of evidence, using the visible aftermath to uncover the nature of the unseen cause. The universe's first chemical factories were built and operated in the dark. But their product, carried on the bones of ancient stars, shines a light on the entire process. We're at the edge of a new era in cosmic discovery. The story of the first galaxies, it was theory, simulation. Now it's about to be tested with real data. The James Webb Space Telescope gave us those first glimpses of the cosmic dawn. But that's just the opening act. A suite of next-generation tools is being built. In space, on the ground, they'll peer deeper, see sharper, listen more carefully than ever before. They'll transform our understanding of that foundational epoch. The moment the invisible scaffolding was first illuminated, the next great eye in the sky will be the Nancy Grace Roman Space Telescope. Webb is a deep field specialist. Roman will be a cosmic surveyor. It's built to capture enormous, sweeping portraits of the sky. Its field of view is 100 times larger than Hubble's. So it won't just find a few ancient galaxies. It will find millions. It will conduct a vast census of the infant universe, map out where these early structures were, how they were distributed, how they evolved over hundreds of millions of years. That statistical power is crucial. It will show us the rules, the patterns that governed galaxy growth. With Roman's data, we move from studying individual examples to understanding the population as a whole. We'll see the full tapestry of the cosmic dawn, not just a few brilliant threads. On the ground, a new generation of optical giants is rising. The European Extremely Large Telescope, the ELT. Its primary mirror will be nearly 40 meters across. That's larger than a basketball court. That immense light-gathering power lets it do something extraordinary. It won't just see ancient galaxies as faint smudges. It will begin to resolve their internal structure. We might see the first swirling disks, the first clusters of stars. The first signs of how these infant systems were organized. The ELT will bring the cosmic dawn into focus, transforming abstract points of light into recognizable galactic shapes. It's like switching from a blurry snapshot to a high-definition portrait of the universe's youth. But light is only part of the story. To understand the era before the first stars, we need to listen. And that's the mission of a revolutionary radio telescope project, the Square Kilometre Array, the SKA. It will be the largest radio observatory ever built. Thousands of antennas spread across 2 continents. Its primary goal for cosmology is to detect a whisper from the primordial fog itself, the 21-centimeter line. A faint radio signal emitted by neutral hydrogen atoms. Before the first stars, the universe was filled with this neutral hydrogen. As the first galaxies ignited, their ultraviolet radiation began to burn holes in this fog, ionizing bubbles around them. The SKA aims to map this process in 3 dimensions. By detecting the subtle changes in the 21-centimeter signal across the sky and across cosmic time, it will create a movie of reionization, a direct view of how the first lights pierce the darkness, galaxy by galaxy, bubble by bubble. This map will be the ultimate test of our dark matter models. It will show us exactly how the invisible scaffolding guided the lighting up of the cosmos. Together, these missions are a coordinated assault on the greatest mystery in structure formation. They'll provide data of such precision that we can move from informed speculation to direct observation. We won't just infer the properties of dark matter from its effects. We will watch those effects play out, in real time across billions of light years. We will witness the universe's first chapters being written, and in doing so, we may finally read the signature of the hidden author. The future of this story isn't just about more powerful telescopes. It's about finally seeing the dawn for what it truly was. It forces a humbling shift. We aren't the main characters, we're a late afterthought. Every atom in your body, every element heavier than hydrogen, was forged inside a star. A star that lived and died long before our sun was born. And that star itself was only possible because an immense, invisible halo of dark matter gathered the gas to create it. Your existence is a product of that ancient architecture. The chair you sit on, the screen, the air you breathe. All of it was assembled by gravity's invisible hand. We aren't just in the universe, we are of it. Literally, physically. And most of what constitutes that universe is something we fundamentally cannot perceive. That challenges a human instinct. We trust our senses. We believe what we see and touch is the full extent of reality. Cosmology tells us that's an illusion. The glittering night sky, the spiral of a galaxy, the light of our sun, that's just decoration. The visible universe is the froth on the surface of a deep, dark ocean. The real substance, the mass and the structure, lies beneath, in a form that doesn't interact with light. Our entire reality is built on a foundation we are blind to. It's as if we spent our lives admiring a painting, only to realize the canvas itself is made of a material we cannot comprehend. It holds the image in place. This isn't just about a missing puzzle piece. It's realizing the puzzle we've been trying to solve is only a small part of a much larger, hidden picture. That makes the search for dark matter more than science. It's a philosophical quest, the human drive to understand our true context, to answer the basic questions. What is the world made of? Why is it structured this way, our place within it? For millennia, we looked to the stars for answers. Now we must look into the darkness between them. The pursuit forces a kind of humility. It acknowledges the universe operates by rules, is composed of substances that may forever elude our direct experience. Yet, paradoxically, by studying the effects, the way galaxies spin, the way light bends, the ancient patterns in the first light, we can infer the presence of this hidden world. We are using the visible to decode the invisible, reading the story by studying footprints in the sand, even though we cannot see the creature that made them. This leads to a profound connection. The same mysterious substance that sculpted the first galaxies billions of years ago also sculpted the conditions for life on a small, rocky planet. The dark matter halo of the Milky Way is not a distant abstraction. It is here, now. It envelops our solar system. Trillions of these unknown particles are passing through you as you listen to this. With no effect you can feel. You are, at this moment, immersed in the ancient architect. It is the most intimate and distant thing imaginable. So understanding dark matter isn't just about the far reaches of space and time. It is about understanding the hidden framework of our own home, our own existence. The quest to find it is the quest to finally meet the silent author of our cosmic biography. The cosmic dawn wasn't uniform, it was a patchwork. Different beginnings, all depending on the invisible geography of dark matter, where a halo formed in that early web decided its fate. The cosmic web was like a three-dimensional map of gravitational potential. Some places were like deep valleys, where multiple dark matter filaments came together. The intersections, the gravitational pull there was strongest, those were the hubs. Dark matter flowed into these knots from several directions at once, building massive halos very quickly. When the primordial gas finally started to move, it had multiple highways feeding into these central spots. The gas arrived in torrents. It created dense, turbulent reservoirs. High-pressure environments, cosmic metropolises under construction. Here, star formation could explode in furious bursts. These are the likely birthplaces of those surprisingly massive, bright galaxies that JWST sees from the first few 100 million years. The conditions were also ripe for something else. The rapid inflow of so much gas to the center of such a deep gravitational well could have directly fed a massive black hole seed. Whether it was primordial or from a collapsing supermassive star, the hubs became the engines, but not every halo formed at a busy intersection. Most were along the quieter stretches of the filaments. The cosmic suburbs. Here, dark matter accumulated more slowly from a thinner stream. The gravitational well was shallower. Gas trickled in at a steadier pace. These halos gave rise to smaller, more modest protogalaxies. Their star formation was less explosive, more prolonged. They were the villages. Their growth was organic, often needing later mergers with neighbors to become anything significant. Then there were the truly isolated halos. Out in the cosmic countryside, far from the dense filaments, these might have gathered just enough gas for a single generation of stars before their fuel was exhausted or disrupted. They remained frozen in time, tiny fossils. This initial diversity was then amplified by feedback. A massive, brilliant galaxy born at a hub didn't just shine in isolation. It flooded its entire region with torrents of ultraviolet radiation and, eventually, supernova shockwaves. For a smaller, neighboring halo trying to form its first stars, this was a catastrophe. That intense radiation could heat its gas, preventing it from cooling and condensing, or it could strip the gas away completely, blowing it back into space. A promising protogalaxy could have its growth stunted or even terminated before it truly began, just because it had a luminous, violent giant for a neighbor. Its dark matter halo remained, a silent, empty scaffold. This process likely explains why we see so few small satellite galaxies around our Milky Way compared to what the simulations predict. Many were starved by the early brilliance of the Milky Way's own progenitor. So the rich tapestry of galaxies we see today, majestic spirals, giant ellipticals, countless faint dwarfs, was woven from these first decisions. The initial random placement of a dark matter halo on the cosmic web set its starting conditions. The subsequent interactions with its environment, shaped by the light and fury of its neighbors, determined its path. A halo born at a busy intersection, if it continued to merge and accrete efficiently, could become the core of a future giant elliptical. A halo in a quieter filament, if left to grow steadily without catastrophic disruption, might develop the ordered rotation for a beautiful spiral disk. And those small, quenched halos, they are the ultra-faint dwarfs we see today, each holding a few ancient stars, a silent testament to a harsh beginning. The variety isn't random. It's the direct legacy of the invisible architecture laid down in the darkness, and the complex, often violent story that unfolded when light finally entered. Even the invisible architect has limits. Inside a growing galaxy, something shifts. Dark matter built the stage, but the actors start changing the set. For billions of years, its gravity was the supreme force. It dictated where everything would go. But deep in a mature galaxy, in the core, ordinary matter finally takes over. Stars form in dense clusters. Gas cools and collapses into disks. The density of all this luminous stuff, the baryons, becomes so immense. Its own gravitational pull begins to rival the dark matter halo. Then it surpasses it right at the center. That's baryonic dominance, a cosmic changing of the guard. The ghostly foundation is still there, enveloping everything. But downtown, the visible universe seizes control, and this shift unleashes a new physics, a dynamic, often violent, rewriting of the rules, because stars aren't passive. They're engines. They blast out radiation and stellar winds. The most massive ones die in supernova. They shake the fabric of the galaxy, and at the very center, a supermassive black hole might lurk. It feasts on gas. It erupts in titanic outbursts. All this activity, stellar feedback, black hole feedback, it pumps tremendous energy back into the environment. It heats the gas. It creates powerful shockwaves. That energy doesn't just affect other stars and gas. It also interacts with the dark matter itself. Think of the galaxy's core as a crowded dance floor. The dark matter particles are like slow, ghostly dancers. They orbit in predictable paths. The baryons, the stars and gas, are like energetic dancers, fast-moving, constantly bumping and shoving. Through complex gravitational interactions, the energetic baryons can transfer their energy. They give the dark matter particles a gravitational kick. That process is called dark matter heating. Over cosmic time, these repeated kicks can push the dark matter particles outward. They scatter them from the very center. They smooth out the sharp, dense peak of the dark matter halo, the one simulations predict. In its place, a shallower core forms, more constant in density. The invisible foundation is literally sculpted by the light and fury of the stars it helped create. It's a profound reversal. It marks the moment the visible universe gains agency. For eons, dark matter's silent gravity wrote the story. Now, within the brilliant cities it built, the story is being edited. The legacy of the first light isn't just illumination. It's a force of reorganization, a galaxy's final structure. The shape of its core, the distribution of its stars, even the orbit of its suns, it becomes a product of this long dialogue. The invisible hand built the theater, but the play itself, with all its drama and energy, begins to rebuild the walls. The ancient seeds grew in the dark, and now we live in that cosmic forest. That first light wasn't isolated. It started a chain reaction. It's been going for over 13 billion years. Those early dark matter halos where the first stars formed, they weren't endpoints. They were the first building blocks. The universe was under construction. Gravity was the architect, patient, pulling things together. Halos collided. They merged. Small protogalaxies combined into larger ones. This process, this hierarchical assembly, it's the central engine, the engine of cosmic growth. It never really stopped. It's still happening now in slow motion. The great galaxy clusters we see, with thousands of galaxies each, they're the modern result. This relentless merging, they sit at the densest intersections, the densest parts of the cosmic web. They're the direct descendants of those first massive hubs from the dawn of time. And the sprawling filaments of galaxies stretching across the void, they are the evolved version, the grand-scale version of those faint dark matter rivers. The rivers that first channeled the primordial gas. The universe today is a mature version of its infant self. The blueprint was laid down by dark matter in the first few 100 million years. It's just been magnified since then, filled in by eons of stellar life and death and gravitational attraction. We can read this history. Its pages are written in starlight. In spatial distribution, take our own galactic neighborhood. The Milky Way is surrounded by a swarm of small satellite galaxies and ancient globular star clusters. These aren't random hitchhikers. They're fossilized remnants of earlier mergers, the surviving cores of smaller galaxies consumed long ago. Their stars carry a distinct chemical signature. It tells us they formed somewhere else, under different rules, before being assimilated. By mapping these ancient stars, their motions and compositions, astronomers can do a kind of galactic archaeology. They can peel back the layers of our galaxy's growth. They can identify distinct merger events that happened billions of years ago. Each event added stars, it added gas, it added more dark matter to the growing Milky Way. It shaped the final spiral structure. Our galaxy is a living record. A record of its own assembly. And that assembly began with those first tiny halos. On the largest scales, our telescopes map millions of galaxies, their three-dimensional positions. This map from a sufficient distance reveals the cosmic web. In stunning detail, the same filamentary structure, the same vast voids, the same rich clusters. The clusters that simulations of dark matter predict. This large-scale structure isn't a modern invention. It's the final expression, the elaborate expression of the initial conditions. Conditions imprinted at the very beginning. The pattern we see today is a direct link. A link to the quantum ripples of the inflationary epoch, amplified by the gravitational influence of dark matter. By measuring this web, its precise statistical properties, how galaxies cluster, the sizes of voids, the thickness of filaments, cosmologists can test our understanding. They can refine our understanding of that invisible component. The universe's present architecture is the ultimate validation of the story that started in the dark. So when you look up at the night sky, you're not just seeing points of light. You're looking at the mature outcome, the outcome of a process that started with an invisible whisper. Every galaxy, from the grandest spiral to the faintest dwarf, is a chapter in a single, continuous narrative. The dark matter that shaped the first faint glimmers is the same substance. The same substance that holds the modern cosmic web together. To understand the brilliant cities of the present, we have to decipher the silent blueprints of the past. Our quest to map the heavens today is in essence an attempt to read the opening lines of our cosmic story, written in the language of an unseen architect. Our universe has a story, but it's told by what we can't see. We've followed that story from the first quantum whispers all the way to the cosmic cities we see now. We traced a line through the dark. The only clues we had were light and gravity, and that journey shows us something. It's a humbling truth. The brilliant, star-filled cosmos we look at, it's not the main event. It's more like a magnificent afterthought, a luminous detail. It's painted onto a canvas that's woven almost entirely from dark matter. Those first galaxies weren't random accidents. They weren't just chaos in a void. They were the inevitable offspring. They came from microscopic quantum fluctuations. And those fluctuations were nurtured for eons by an immense gravitational force. An invisible force. It gathered the raw materials of existence in total darkness. It waited, and then it finally sparked the first light. Now we're standing at the brink of something new. We have eyes like the James Webb Space Telescope. The next generation of observatories, we're closer than ever to directly witnessing that cosmic dawn. We'll watch in unprecedented detail as the invisible scaffolding is first illuminated. Every new observation is a piece of a code. It's the ultimate code. And that code may finally let us decode the full nature of our mysterious architect. So the next time you look up at the stars, remember, you're not just seeing points of light in a vast emptiness. You're seeing a legacy, the legacy of something you cannot see. It's the final glowing signature, the signature of a hidden hand that shaped everything from the very beginning.